Okay, I can see most people have not joined, so I can proceed. The expectation, let's move to the next slide of my presentation. My presentation outline is going to start from the introduction section and to run through to the conclusions or the major findings of the topic that has been shown so far at the first page of my slide. I have a lot of slides, which is 38 slides, but I think it's too much, but don't bother a lot because it is dominated with a lot of pictures. So I will speak from pictorial point of views rather than boring you with a lot of theoretical concepts. So definitely you are going to appreciate my presentation. My introduction. The satellite imagery, as we are all aware, or as an expert in the concept of remote sensing, has really gained wide applications, including but not limited to disaster management. That is where people are using satellite images to detect especially flood-prone zones and other disasters like heat waves and drought zones, depending on the context. Agricultural development, we have also been using the concept of satellite image for agricultural development and also for sustainable urban planning. And when it comes to the environmental monitoring aspect, I will use my country, Ghana, as a case study. The devastating of illegal forest areas because of illegal mining activities is alarming. And therefore, we are flying drones and other remote sensing technologies just to detect the various illegal mining activities and also compare the change detections from years to years so that we can come out with a reasonable conclusion as to how the land is being devastated by these illegal mining activities. We all know that the applications of satellite imagery over the years, what we normally do is we require manual identification of features and spatial objects in the imagery. And that is where we as remote sensing, we have been doing over the previous list. We look at the image by visual inspection, then we assign some spectral signatures to some features in the image so that we can classify some features into distinctive classes. And we can all attest to the fact that we cannot live away with human errors. So to minimize the human errors, we are trying to adopt into the modern concept of training algorithms to perform such tasks for us. And people have come out with various algorithms in the concept of deep learning, but the focus here is we know how to see how these algorithms are performing to classify satellite images by means of convolutional neural networks. Now, the major question at stake is how can we explore the complex challenge of multiclass image recognition? And the next question is which algorithms is performing better compared to others when it comes to the concept of urban planning? And how can we evaluate the predictive performances, that's the efficacy of these algorithms, in terms of classifying spatial features in satellite images? This has brought us today, and this is the major questions we are trying to come out with. Let's address how we can evaluate these major questions based on my aims and objectives. The concept of this one is to evaluate wide range of convolutional neural architectures as to come out with a reasonable conclusion as to which one is performing better. So our main aim for this project is to experimentally evaluate deep learning convolutional algorithms for analysis of land use cover mapping using a multispectral satellite data set. However, our specific objectives are one, we have to create some deep neural networks for existing architectures. So, popularly among the one, in our work, I and Professor Engineer Han decided we are going to explore more on the concept of maybe 10 convolutional neural networks. But we realized that for the time factor for my thesis frame, we cannot accomplish that. So we have to reduce it to at least some 6 or 5 popular neural networks and make a detailed comparative analysis as to how best they are performing. So first of all, we considered UNet, SedgeNet, ResNet 18, ResNet 50, Exception, and inception in our case. Then our objective B is how are we going to train these neural networks to perform the automatic land use land cover classification. So that is why I say the next B is to train and optimize the configurations of the neural networks to perform automatic land use land cover classification. And our C objective is to evaluate the performance of these neural networks based on accuracy metrics. I would like to talk about the data we use in our case. This thesis was based on the Deep Globe satellite data set. That is from the Computer Vision 2015 database. People have come out with a lot of ideas concerning this particular data, and researchers are showing that if you use it, you could get a very low in terms of minimizing errors of classification. So we coupled with Google, in addition with Google, which is a company, a subsidiary company of Google, so that we can get access to this data, which has already been processed and labeled according to the various classes. And this spatial data is a multi-spectral data collected by WorldView sensor with a spatial resolution of 50 centimeters per pixel, which is also approximately 0.5 meters per pixel. Within the data, you need to annotate the various land cover classes within the data. So looking at my extreme right, you could see a table on the heading land use cover annotations and the description of the various classes. So when we are using the term urban, then we are referring to the various man-made or built areas with human artifacts. But let me chip in here, we are not classifying roads for now. Then we also use the concept agricultural land, which refers to plantation, regular farms, acres, cropland nurseries, and also range referring to grasslands, some greenhouse and non-farming and non-forest zones. And forest zones are depicting trees and canopies, while water bodies are referring to all water, rivers, and wetlands and ponds in our case for this special data. Then we also use the concept of bare land, which refers to no vegetation areas, mountain or rocky areas. Then one thing I will also talk about is the unknown. As a remote sensing specialist, especially when you are dealing with the concept of optical remote sensing technology, you could experience some weather conditions such as cloud covers, as to compare to radar satellite where it is unaffected by weather conditions. So in our case, we are using optical remote sensing techniques here or data here. So definitely some of the data will be interfered by cloud covers. So we use unknown to depict the areas that has been interfered by clouds during the data acquisition stage. I just put in here some of the samples of the data so that everyone could have an idea of how the data looks like. Extreme left, you can see the satellite image. And let me use my pointer here. I think everybody can see. You can clearly see some clouds cover here during the data acquisition. And in my labeling or the annotation stage, the darker sections here is depicting the unknown or the cloud covers within the data set. And I was using blue color to depict the various water bodies as seen. And this will be more expressed when we start our predictions in the subsequent slide. The convolutional neural architectures has a lot of frameworks everybody can use. Familiarity, I am familiar with. We can talk about TensorFlow, Python, which I'm also familiar with, and Scikit-learn and MATLAB. But this work was focusing on using the MATLAB-based framework to explore a wide range of convolutional neural architectures. But before you use this, you have to understand that there are some special inbuilt toolboxes you have to install before you can proceed. Some include, or some important toolbox include the deep learning toolbox, the image processing toolbox, the computer processing unit coder, the optimization toolbox, the computer vision toolbox, because we are dealing with image recognition, and statistics and machine learning toolbox, because you are going to deal with a lot of statistical concepts in this remote sensing techniques we adopted during my master's thesis. I'll go to the methodology section, which is a very critical aspect of the whole work I am presenting today. First of all, the data pre-processing stage. Every convolutional neural architecture has an image size it can take in before trying to extract relevant information. And therefore, your coding or your Python or your MATLAB scripting has to be very, very important here. So you have to write a script to resize all the satellite images you have and the various corresponding labels accordingly. That is the data processing stage. The next stage is the data preparation for training, validation, and testing. In my case, I was using 803 images for this segmentation task. So I split the data into the ratio by using 80% of the data to train the neural network and 10% for validation and also another 10 for testing. The reason is that you can see that the higher percentage of the data has been allocated to the training section because the architecture of neural networks, some has deep convolutional layers, said that it has to take more data before you can train them and get an optimal result. So much of the data section has to be spread well, said that large amount of the data could be used for training of the neural networks. And I also talk about the framework using the MATLAB briefly. This is people to have a fair idea of the various MATLAB scripting or the code that goes in here. It's a lot, but I don't want to bore you with a lot of time in explaining the code aspect. So first, you have to create a convolutional neural network models through your MATLAB scripting. Then define the names and specify the class IDs. In our case, we are using 7 classes. So we have to give special IDs in the form of RGB, which we used in our case. Then balancing the classes. This thing seems very awkward when you are talking about balancing the classes in the context of remote sensing. You know that when you are training a neural network, the neural network assigns specific weight to every classes in the data set. So you have to ensure that at least higher percentage of every weight is assigned to the various classes to prevent bias when you are making your prediction. Then you have to set training options for training the neural networks. There are certain hyperparameters like the initial learning rate, the airport, the minimal batch size. You have to tune them to a certain level until you get an optimal result. And this is the key aspect of the whole work of deep learning. Because if you did not get your hyperparameters tuning well, it could end up you getting a very low accuracy as you are expecting for your work. Then my last methodology is to evaluate the trained neural networks to select the best performing algorithm. Still on my methodology, let me still try to open up in terms of describing how certain things were done in my case. Resizing all the 800 images just to satisfy the conditions of the convolutional neural network. That is where your MATLAB scripting or your Python coding has to come here, like I said earlier. If you look at the various image sizes here, in my case, that is what I used. And the 222 4x224 by 3 are using RGB. So the 3 here is standing for the channel of the image because it is a multispectral. And this input, I use the 224 for ResNet, residual neural network. That is the image input it can take. 299 is for SageNet, and 512 by 512 is taken by UNet in this case. Let's go to the training session of the neural networks. I said earlier that the most important thing is the splitting of the data during the concept of deep learning. You could have all available data and unique data, unique labels, but if you did not partition your data set very well, you cannot accomplish your goal. And therefore, in my case, having 803 satellite images I splitted the images of using 600 images specifically to train the neural network, and testing of the neural network for using 203 images. What about the training? The training requires that how is the model that you are making the prediction is fitting to the ground truth data you are using. And the testing is explaining that, okay, now I have a new set of images. How will the model that I have built predict the new set of images maybe I have? And that is why the testing and the training is an important or a principal component of this deep learning concept. So when you are splitting, you have to be careful of how best you are going to split your data. You cannot talk about the principle of deep learning by not talking about the challenges you encountered. As we all know, coding requires a lot of challenges, and you should not be expert, but at least know whatever you are doing. So the first challenges I encounter was the errors associated with creating the different convolutional neural networks during the execution of the code. I quite remember how UNet was giving me a tough time in terms of using MATLAB framework. So it came to a time I had wanted to use Python for that, but the concept of ROS was based on MATLAB. I could not use a MIS framework. So I quite remember UNet was the only network that was giving me a lot of headaches, but I was able to accomplish my tasks. Then you have to, some section of the code, you have to make some additional changes before you can run some convolutional neural networks. That's why I was saying that if your coding is not good, you should not go into the concept of deep learning, because sometimes the headaches can even disrupt you from achieving your aim. Then one requirement is the computer memory. You need significant amount of memory to train complex deep learning models. And that was a major task for my case. So I have to seek for the attention of the university to increase my memory. Then one major thing I detected was that the range class, among all the various 7 classes, detection of the range class in the data set was the most difficult part in my study. Having said briefly about my methodology, I would like to go into the workflow session just to have a breakdown of whatever it was done. The first stage involved the image processing stage, where you are going to resize the various images you have acquired to suit the conditions of the convolutional neural network inputs. Then you have to split the data. Like I said, splitting of the data is a key component here. I always stress, because splitting of the data can lead you afar when you don't know what you are doing. So you have to pay much attention when you are splitting your data for training, testing, and validation. Then you have to create neural networks. Depends on the framework you could use. In our case, we are trying to explore wide range using MATLAB. So I have to script for the various convolutional networks I have mentioned using MATLAB and perform my 2D semantic segmentation. But I brought this one here because the various network I am considering has various architectures. That's why I have put these drawings there or diagrams here, so that people will have a fair idea of the various architectures of the network I trained. And basically, we have segmented base and pixel base. If you look at a special kind of deep lab, which is an input of ResNet, inception, and exception models, they classify imagery based on what we call using pixel-based layers. And segmentation-based layers refers to maybe units and other SegNets. So we are making a comparative analysis between the various neural networks I have mentioned earlier so far. And one of the key aspects here is to set training options. The training options is where you have to tune some parameters until you get an optimal result so that it will make a prediction. How are you going to optimize the convolutional neural networks? One of the key important aspects you have to tune here is what we call the initial learning rate, the number of epochs, and the minimal batch size. The minimal batch size has a relation with the computer memory you are losing. So you have to pay much attention when you are tuning your optimal parameters. That is why I will always advise that you have to read a lot of literature on what people have done when they are training their convolutional networks, which is related to yours, before you can come out with an optimal result so far. Then the next stage is we need to evaluate the various convolutional neural network. That is the component of how this work is reflected upon. Because the key component of this work is to evaluate convolutional neural networks and see which one is performing better using a MATLAB-based framework. I'll not bother you with a lot of theory, like I said, when it comes to the concept of evaluation accuracy matrix. So briefly, I will just explain here briefly so that people will have a fair idea. If you talk about the classification accuracy, we are talking about percentage of collective predicted pixels for each class in the image. Then the weight assigned, we also have when the weight is more placed on how best we can get the prediction of the original inputs and the accuracy of the predicted or the ground truths, we use the term weighted intersection over union. So how is your prediction fitting the original data that you imputed? Okay, you have to use the concept of intersection over union here. Then the testing accuracy. You cannot evaluate deep learning by not talking about the testing accuracy, because it is telling us that when you have a new images, how is the model predicting to that new image? So the accuracy reflected on the entire data set of the test is called testing accuracy. Then the training loss. Every deep learning has a loss functions. In our case, we need to indicate how the model is fitting to the training data. And that could be well described using the term training loss. Because after making the prediction, the loss function can also determine how best the algorithm is performing. So all these are the various accuracy indicators I use in my case to evaluate the performance of the neural networks I investigate so far. This is the experiment I use. My model was trained on a single GPU from the University of Applied Sciences. And it was a high-speed virtual machine with 12 gig CPU. So you can sit at your comfort of your home and still run your model. Like I said, I used 128 gigabyte because at first I was using around 50 and it was too bad because it came to a time where the MATLAB version has to even crashed. So I have to consult my university for a very new update of the RAM so that it could speed the processing steps of the deep learning training. And I used 2 Xeon Gold, which is one of the most central processing units if you want a fast processing in terms of image segmentation tasks using the concept of deep learning. So this is a fair idea of the training models I used and the computer specifications for training my model. I stole this from the MATLAB networks. When you start training, all this will start popping out to give you a fair idea of the architecture of the various neural networks. But I don't want to go into detail here after the presentation. The reason is that all the things happening here becomes abstract sometimes. And I just put it here so that you could show you the architecture of SegNet and the various convolution and the pooling operations going in here. The convolution and the pooling operations operate in such that whenever the input data is being sent into the neural network, SegNet, for instance, has two types of characteristics, encoder section and a decoder section. What the encoder does is that it tries to receive the input image. And when it has received the input image, it tries to go through a lot of pooling operations and extract relevant parameters from the image. Then it has a special characteristics or two called that the decoder. The decoder will try to upsample. That is, it will gradually increase the spatial resolution of the image within the neural network. These are inbuilt, which cannot be seen with your eye, but you have to understand the concept. And when it increases the spatial image, it makes it possible to extract relevant features and use the term upsampling. So the essence of the decoder is to upsample the image to give a reliable output. Here's a typical graph for training a neural network using a MATLAB-based framework and the optimization. Looking at the graph, the blue sections is telling us the training part of the entire deep learning model. So I use SurgeNet for my case. And why it is training, I told you, you should know the loss function, because achieving accuracy or reliable accuracy will also depend on the loss function. So I put this table one there to compare the validation accuracy and losses of the various neural network which I used in my case. And looking at the table in my extreme right, it is clearly seen that ResNet 50 had a validation accuracy of 80.66, and it achieved a minimal loss compared to SurgeNet, which was even though achieving higher classification validation accuracy, but with a very higher loss. So comparatively, when selection, you have to take selecting for the best algorithm, you have to take into consideration all validation accuracies and the minimal loss incurred during training of your model. I've come to the result and discussion section. These are going to be pictorial views. The center of the whole work is to evaluate, like I said. So you have to train a lot of images so that you can come out with a reasonable conclusion. So I assigned some IDs to the test data. So I call this test data 93. Extremely here, you can see the original image, and my cloud is here. When you impute this image on the label, let me go back and show you the label here so that people understand what is happening. Good. How the convolutional network works is that when you impute your satellite image after you have resized it based on the conditions of the neural network, it will overlay this image on the label. So when it overlays these images on the label, it will come out with a prediction which we call the ground truth. Let me go back to my result and analysis. Good. So when it overlays this on the label, as I showed in the previous slide, it is going to make a prediction. And that prediction is going to be based on the input of your stripping code, the IDs you have assigned. So in my case, I was telling the model that, okay, if you see areas with blue sections, classify it as water zones. And if you see areas with white sections, classify it as bare land. If you see areas in the pink section, you could classify it as range, and agricultural lands as yellow, and also urban areas as this color light green over here. So all this is what you are going to tell your MATLAB frameworks and also script it so that it can perform whatever we are doing here. So to not bore you with a lot of talks, and for the sake of time, I train a lot of images like you can see here where we have dense areas and see how the various algorithms are performing. Another images, you can see a lot of urban areas. How is it performing when you are training to make a prediction? Another image which I call test data 25, where you have clustered urban areas. How is it predicting these models? And you have some rocky or agriculture areas mixed with range. How is the model predicting these various classes? And when you have this kind of shady areas mixed with some light forest zones, or how is the model predicting? So you have a river bank with some river crossing here or some water bodies. How is the model predicting all these characteristics? And you have a lot of water bodies or water. How is it predicting? And you can see that every model was predicting differently according to the architecture of the neural networks. So I went on to test a lot of images. I've shown this image before where the cover, the weather condition is also captured in terms of the cloud. Then we also have shady areas mixed with water and a lot of banks, we have to know how the various model is predicting with respect to the ground truth. So I trained a lot of images of 203 just to know which algorithm is performing better. I put there to know, to have an idea of how best the various MATLAB tries to make your classification. So this is a picture of a flame from MATLAB comparing the accuracy levels and the intersection over unions for the various neural networks. But this is clumsy. How can somebody judge this? Make a sound judgment in terms of your evaluation process. So to make it very simple and easy for people to judge the performance prediction of the various neural networks, I try to sample them in the form of a table, as you can see here, so that we could have a detailed comparative analysis of the various classes that was predicted. So clearly seen, you have all the various classes and the percentage of classes being predicted here. Then I also take into consideration the computational time. This is very serious because sometimes, depending on the architecture of the neural networks, some could take about 44 minutes to train a single image. And that means when you are dealing with the concept of deep learning, you have to take into consideration the computer speed and the memory. So if you look at this table, you can see that inception, even though it's predicting better in terms of urban and the others, but look at the computational time. You have to train one image for 44 minutes, 53 seconds before you can get an output. We have come to the table here, which is trying to compare the performances of the various neural networks as captured in my objectives. So I use various accuracy matrices because you cannot base your judgment on only one accuracy matrix. So below my table here, I use some acronyms. Pardon me for that. The acronyms here, when you see GA, I am referring to the global accuracy. MCA, the mean class accuracy. MIU, the mean intersection over union. How is the model you have imputed? How is the prediction of the model in respect to the ground truth or the actual data on the ground? That is why you have to consider the mean intersection over union. Then what is the boundary? Does the model that you are predicting or does your predicted model has a strong boundary connections with your input data? You have to take also into consideration. That is where the boundary score measure comes in here. Then one thing is, how is the weighted intersection? Being placed a lot of emphasis on the weight so that the model will try to predict based on equal weight. We have to do what we call weight initialization so that the various models will predict the various classes by assigning all of them with an equal weight to make your prediction. So we also considered weighted intersection over union as part of our classification or accuracy metrics. Then you have to validate your model. So we also include VA here, which you can see here, also called the validation model. Then the test accuracy. You have to test your model that you have created. So I also use the term TA and the training loss, as the training loss is also a key factor to know the loss functions as which the various models are performing. Now, the expected outcome of the whole thing is the key component here I would like to explain. But I bulleted only 4 of them. Sorry, we have only 5 of them for the sake of time, so that I will not bother you with a lot of stuff. State-of-the-art deep learning convolutional algorithms were created to take in data and generate reliable math automated analysis. I know people have come out with a lot of ideas in terms of using different frameworks, like I said, PyTorch, TensorFlow, Python libraries, scikit-learn. But I sat down in collaboration with my professor and said, okay, let's look at some popular deep neural networks like UNet, SegNet, and explore all this using the context of MATLAB. So we have to create deep neural network that can take all this data and scrape a lot of 803 images to suit. So our first conclusion is that we have created a state-of-the-art deep learning convolutional model which can take in reliable data to perform automated analysis of satellite imagery. And improved mapping results we also obtain by adopting stochastic gradients from existing deep learning libraries. The conclusion is straightforward here in the sense that a lot of deep learning optimization algorithms exist. Typically among them, you can talk about the adaptive moment optimization. So somebody can also sit down and also try to hammer on this work by also using the concept of adaptive moment optimization. That is why research is dynamic. And we don't come with a specific idea. We all try to explore ideas so that we can come out with a reasonable conclusions in the context of modern remote sensing. But overall, looking at my work, we had that the deep learning models, the most one performing better was the deep Lavin3, which is the inception, exception, the ResNet 18, and the stops. Those are the models that were performing better than the pixel levels or the fully connected layers like UNet. And this can be seen straightforward from my table. And in all, we can see that ResNet 50, which is the ResNet residual neural network introduced by Kaiman Hill, having about 15 neural network, was emerging as the best model for multiclass segmentation. And SegNet, we also realize that is very, very computationally inexpensive though. So when you are training SegNet, it will not take like that time. But we realized that inception model was taking much time, and therefore it is the one with the major computational costs than the other methods that were investigated. So in conclusion, let me chip in. This is not a general conclusion worldwide. This conclusion is specifically based on the deep blue data set. The reason is that, like I said, research is dynamic. People can also use different data sets and they could have different results, which is different from what I have had. So the overall is that people can also reflect or review using adaptive moment, test it with different data, and also come out with reasonable conclusions, as I have done using the digital group satellite multispectral satellite data set. So, audience, this will be the end of my presentation. And thank you very much, because these are some of the key references I use. So I will thank you first of all for giving me this platform to share my ideas on the concept of building an approach to evaluate deep learning convolutional algorithms. Thank you once again, Professor Lale and your group, for this opportunity given to me. So thank you.